Hey, good morning.
Morning, Professor Belling. How's it going?
Good. How are you?
Good. I think I'm ready.
I like your jacket.
Thank you. It's my grandfather's.
Pretty cool. Do you want to make me co-host just in case?
Sure, I can do that. Okay. I've set it up to auto mute people when they join, so hopefully there's no, interruptions as people join. But hopefully the other professors are aware of that, just so they can unmute themselves.
Sounds good.
Can you guys hear me okay?
I do.
Okay.
Okay, so we have Mool, John. Guess we're waiting for Pisang Lee and Josh, right?
Yeah.
Yeah, let's wait another minute.
Professor Choi, I have the auto mute on when you join, just so that you're aware.
I think it's fine now, right?
Yeah,
You can hear me, right?
Yep. Nice, Professor Lee. Professor Lee, I have the auto mute upon joining on, just so you're aware.
Okay, so I think we have everyone here. So let's get started. So welcome everyone to George's PhD defense. Please mute yourself while George is talking. And I think we want to get started, George. Are you ready?
Sure, yeah, I'll share my screen. Let me just get that set up. Okay, can everyone see that okay?
Yeah. Do you want to go in full screen or want to
Yeah,
leave it like?
I'll go in full screen. Is that still showing up?
Now it's good. Yeah,
Okay.
please go ahead.
Okay, thank you all for joining me for my doctoral dissertation defense. The topic of my thesis is laser annealing of carrier-selective layers in high-efficiency photovoltaic devices. I'd like to thank my proposal committee, my advisor, Mul Gupta, my chair, Andreas Spelling, Professor Josh Troy, Professor John Offeld, and Professor Q-Seng Lee. Funding for my work primarily came from the National Institute of Aerospace and the NASA Langley Professor Program. So here's a quick outline of what I'll be discussing today. First, I'll go over my motivation, some background on the topic, and my experimental setup. Then I'll discuss laser annealing of TiO2 electron transporting layers for flexible perovskite solar cells. After that, I'll discuss laser annealing of polysilicon for TOPCon carrier-selective contacts for silicon solar cells. Then I'll move on to laser annealing of carrier-selective molybdenum oxide and titanium oxide layers for silicon solar cells. Following that, we'll change gears a bit and discuss the impact of pulse laser heating on silicon passivation and degeneration of defects. And lastly, I'll discuss a laser direct wafer bonding method for solar cell devices. And then I'll discuss the conclusions in any future work. So a primary motivation for this study is the levelized cost of electricity. What the LCOE is basically a sum of the costs of investment, operations, maintenance, and fuel. Obviously, for wind and solar or other renewable energy, there is no fuel costs. And this is divided by the sum of the total energy produced in a given year. You can see for solar, historically, it's had relatively high prices, but in recent years has dropped below all of these other forms of power generation technologies, at least at the utility scale. And it's predicted to further decrease based on the projection from its previous rates and become even cheaper. However, to decrease this levelized cost of electricity further, you can either decrease the cost of fabrication for the device or increase the solar device efficiency. So what are the next generation photovoltaic devices? First, I'll go over a traditional silicon solar cell on the left there. You can see that it has this is an ALBSF structure, so a back surface field. It also has a PERC front structure. And their efficiencies are limited to around 20% on average. And they don't use any sort of carrier-selective layers in the device structure. In the top middle, you can see a perovskite solar cell. When I say perovskite, I'm talking about methylammonium lead triiodide-based perovskites. And this has electron and hole selective layers on either side of the perovskite, which enable carrier selectivity. They have a record efficiency of 25.5%. In the top right, you can see a TOPCon-based silicon solar cell. These used a heavily doped polysilicon layer at the rear for carrier selectivity, and they have a record efficiency of 24.6%. In the bottom middle is a heterojunction silicon solar cell. These use intrinsic amorphous silicon to passivate the silicon absorber, and then heavily doped P and N amorphous silicon for carrier selectivity. And these have, of the single junction materials, the highest efficiency of 26.7%. In the bottom right, you can see a new type of heterojunction cell called the transition metal oxide silicon solar cell. And this uses two different transition metal oxides, one for hole selectivity and one for electron selectivity. While these are newer, they've demonstrated efficiencies of 20.7%. So what is carrier selectivity? First, I'll go over a traditional diffusion-based homojunction electron selective contact. This is made by diffusing dopants into the silicon absorber, and this induces band bending, which allows the electrons to flow downhill towards the metal contact, while holes will flow uphill towards away from the contact. So it obtains its selectivity to the band bending by doping. Next to that is a tunnel oxide, a TOPCon-based tunnel oxide passivating contact. How this works is it's sort of similar to the homojunction cell, but there's a thin tunnel oxide placed between the N+ region and the absorber, which helps to improve the passivation. The carriers can still tunnel through that barrier, but holes have a difficult time with the band bending and the heightened barrier for them to get to reach the contact. Next to that is a band alignment-based electron selective contact. This presents a large barrier for the holes from reaching the contact based on the work function alignment of the TiO2 with the silicon absorber, but electrons will have an easy time flowing towards that metal contact. Lastly is a band bending-based hole selective molybdenum oxide contact. And here the metal's been swapped out with an indium tin oxide transparent contact. How this works is the work function is actually so high that it induces an upward band bending in the silicon absorber, and it allows holes to sort of tunnel through there to the molybdenum oxide, while putting up a barrier for electrons, preventing them from reaching the contact. So annealing is important for all of these carrier-selective layers. It plays an important role in improving the device efficiency. For flexible perovskite solar cells, TiO2 electron transporting layers typically need a 500°C anneal, which will convert that film to anatase and also densify and hydrolyze the film. And this improves, of course, the device efficiency. In the center, the TOPCon-based silicon solar cell, the heavily doped polysilicon typically needs anneals around 875°C to crystallize this layer, activate its dopants, and improve its interface with the tunnel oxide, resulting in high efficiency. And then lastly, transition metal oxide heterojunction silicon solar cells. These transition metal oxides need annealing to control their stoichiometry, their work function alignment, potentially crystallize the films, and improve the interface with the crystalline silicon absorber. So a quick comparison of the different annealing approaches. The current state of the art is sort of furnace annealing. There's batch furnace annealing, which can take hours or even tens of minutes. And typically the temperatures are between 800 and 1,000 degrees. There's rapid thermal annealing, which can shorten that time span to seconds, tens of seconds, and reach higher temperatures, but can typically only process one wafer at a time. What I investigate is a laser annealing approach, pulse laser annealing, which is a new approach with several distinct advantages. It allows for increased throughput. There's an estimate that you can do a wafer process for a 6-inch wafer in 20 to 100 microseconds, that's right. And this will also decrease the thermal budget of your entire process because you don't have to have a furnace running at elevated temperatures for a long amount of time. Also, the laser has a short pulse width, which means that the heat won't, this is done rapidly and the heat won't diffuse to the bulk. Also, you can change your laser wavelength to allow for localized energy deposition so that the energy only targets the layer or region of interest that you want to anneal. So quick overview of the laser annealing approach that I used. I used a pulsed ultraviolet laser with a wavelength of 355 nanometers, a pulse width of 25 nanoseconds, and a repetition rate of 50 kilohertz. The laser light passes through a beam expander and then into a galvanometer scanner, where it is focused through an f-theta lens onto the sample. The sample sits on a height adjustable sample stage, which can be moved up and down to change the location of the sample within the focus profile of the beam. There's a laser galvo controller, which sends a trigger pulse to the laser and a control pulse to the galvo to keep them in sync. And then there's a computer that runs CAD software to set your line spacing and your shape, and also control the laser power and its repetition rate. So the main benefits of this is that it allows for enhanced efficiency as well as decreased cost. You can see on the right, the laser light only absorbs in a shallow region near this front surface, allowing for localized heat injection. You can shorten your overall cycle process time from furnace techniques by, this can happen, of course, in microseconds or milliseconds. And these short pulses, roughly tens of nanoseconds, allow for rapid heating and cooling. So this annealed area from the laser doesn't diffuse into the bulk. It also prevents any damage to the substrate or the absorber. Because this laser light's only being absorbed in the film, you can prevent any damage to your substrate. Lastly, some focusing considerations. If you move from the focus of the laser, the beam begins to spread out and the intensity of the beam is more uniform. This enables you to have sort of a more uniformity of processing if you want to defocus your beam. However, you can also focus the laser further into your substrate to target different depths of interest. So you could do focused in volume processing by focusing laser somewhere inside your substrate. Or you can even try to process the rear surface by focusing through the front surface at the rear surface of your sample. So now I'll move on to my first chapter, laser annealing of TiO2 electron transporting layers for flexible perovskite solar cells. The key findings of this work were demonstration of a novel laser annealing concept for flexible perovskite solar cells. It demonstrated an efficiency of 17.1% on flexible and rigid glass substrates. It prevents any damage to the underlying polyethylene nephthalate flexible plastic substrate and the indium tin oxide anode. I also demonstrate optical, topographical, and chemical characterization confirming a successful anneal. So why look at perovskite solar cells? If you look at all the various single junction solar cell technologies, You can see crystalline silicon, which is the most popular, has had a steady increase in power conversion efficiency over the years, with its current efficiency record at 26.7%. And then you can look at perovskite solar cells in black here, which popped up around 2013 and have rapidly increased in efficiency and have reached efficiencies of around 25.5% to date. So they very rapidly caught up with silicon in a very short amount of time. So the TiO2 electron transporting layer is the most commonly employed electron transporting layer in perovskite solar cells. This is primarily because it has a low conduction band offset. It has stable electronic properties. It has a high optical transmittance because this is the top layer in the device. It allows light through to the perovskite absorber. The film also has a high durability and an ultra-thin uniformity and homogeneity. The problems with this is that it typically requires an anneal above 450 degrees Celsius for roughly 5 minutes. And this is incompatible with flexible plastic substrates because they'll melt at temperatures that high. Additionally, temperatures that high will increase the sheet resistance of the indium tin oxide anode, and this will result in higher series resistance in your photovoltaic device. Also, this is the highest temperature step in the process, so it increases your thermal budget. The rest of the device can be fabricated at temperatures below 150 degrees Celsius. So there's an interest in replacing this with a pulsed ultraviolet laser annealing method, which will allow for the use of flexible substrates. So the plan with this one was to use a polyethylene naphthalate substrate. It's a flexible plastic. It's coated with an indium tin oxide anode that's been patterned for the device. And then a titanium precursor is deposited onto the substrate, and the laser is raster scanned over the surface to convert the film to TiO2. A quick qualitative optimization of the fluence. You can see on the left, we have the unannealed films on glass and plastic on the top and bottom. They have sort of a blue color. And then in the bottom right, you can see the furnace annealed film on glass. It's become transparent. So that's sort of the conversion that we're after. If you look as the laser fluence is increased, you can see that the film becomes more transparent until a certain point, there begins to appear a moire pattern on both glass and flexible substrates. And this is due to laser ablation. You can also look at this under scanning electron microscopy. What we're looking for here is a good contrast between the light areas, which is the laser anneal areas, and the dark regions, which is the unannealed films. So you can see at low fluences, the spot uniformity is poor and the contrast is poor. As the laser fluence increases, the contrast improves and the spot uniformity also improves. But if we go too far to the 1.64 joules per centimeter squared fluence, you begin to see ablation of the film, and that's what results in that moire pattern. Here's a quick video of the laser annealing process. You can see this is a flexible plastic substrate with the ITO anode and the precursor as it converts from the precursor form to TiO2 with the raster laser scanning. So discuss some optical and electrical properties quickly. So with furnace annealing on the left, you can see that as temperatures get above 300 degrees Celsius, the transmission begins to decrease, which is due to film conversion. This is only at 635 nanometers, but the film, this indicates a film conversion from the precursor to TiO2. And the sheet resistance of the ITO also begins to increase, which is bad. This causes increased series resistance. However, if you look at a laser annealing process on the right, you can see that a similar transmission decrease indicating film conversion occurs. However, the sheet resistance remains constant and low, which is good for our subsequent device. I also did some ellipsometry and X-ray photoelectron spectroscopy to characterize the films. On the top left, you can see the ellipsometry results. Basically, what this indicates is that there's an increase in refractive index, indicating an improved film density and crystallinity that's comparable to the hot plate annealed film. In the XPS, basically we looked at the titanium peaks and the oxygen peaks, and they show an increased binding energy after the anneal from conversion of the amorphous sol gel phase to anatase, and also a decrease in any suboxide peaks, which indicate improved stoichiometry to TiO2 from TiOX. We can then create a device with this. Our device consists of a polyethylene naphthalate substrate, an ITO anode, the TiO2 electron transporting layer, methylammonium lead triiodide perovskite absorber, a spiral-omitad hole transporting layer, and a gold cathode. On the right, you can see sort of the flexible device. It's being bent there, and you can see the 6 different pixels on the device. I then did some illuminated current voltage testing. On the left, you can see the results on rigid glass substrates for both thermal and laser annealing, thermal in red. The hot plate result obtained a 16.6% efficiency, while the laser annealing result obtained efficiencies of 17.1%. Then you can see the result on the right is for flexible plastic, and the efficiency with laser annealing was also 17.1%. So some products of this work, there were 2 publications, one in the Journal of Physical Chemistry letter and one in ACS Applied Materials and Interfaces. We also sent an encapsulated cell to NASA as part of the 11th Materials International Space Station experiment. And I was awarded the 2019 Best Student Paper Award from the National Institute of Aerospace for the work on laser annealing of TiO2. Next, I'll move on to the second chapter for laser annealing of polysilicon, carrier-selective passivation for silicon solar cells. The key findings of this work were that I demonstrated a novel laser annealing concept for state-of-the-art TOPCon structures. I also had some simulation and optical modeling to guide the experimental study. I optimized laser processing to obtain a 718 millivolt IVOC with a subsequent silicon nitride deposition. And lastly, I demonstrate laser activation of dopant and amorphous silicon crystallization. So the operating principle of these cells, again, there's your N-type silicon solar cell in the center in green, and then you have a thin 1.5 nanometer tunnel oxide consisting of SiO2. And on top of that, you deposit a heavily doped polysilicon layer. And once the dopants are activated, it induces band bending, which is due to work function difference between the absorber and that layer, which allows for accumulation of charge at the oxide. The tunnel oxide has a smaller barrier for electrons than it does for holes, which allows electrons to tunnel through easily. And then there's a large number of conduction band states in the polysilicon, allowing for easy electron tunneling. And lastly, there's an induced field effect, which increases the number of electrons at the interface while reducing the number of holes, which prevents any recombination between the 2 at the interfaces. These layers, again, they need annealing. So these results are from our collaborators at Georgia Tech. In the middle there, in the top middle, you can see the impact of sheet resistance with annealing temperature. As the temperature is increased, the sheet resistance drops, which is good. You'll have a lower series resistance, the lower your sheet resistance is. And then on the top right, you can see the impact on the passivation, in particular the implied open circuit voltage. It has a peak value at around 875 degrees Celsius, but higher temperatures begin to degrade the passivation. And this is because what this anneal does is it also crystallizes the film. You can see in A, it's amorphous and the oxide is intact. At 875 degrees C, it begins to become polycrystalline. The oxide is still intact, but if you go further in temperature, you get larger polycrystalline grains, but the oxide begins to break up, which harms your passivation. So again, the issues with this high temperature annealing is that you have the oxide breakup potentially. You can have dopant diffusion. This is a heavily doped region. The dopants can diffuse into your absorber and cause recombination. It's also a low throughput process. The annealing typically takes 30 minutes to an hour. And it's a very high thermal budget step. You have to do this anneal at around 875 degrees Celsius. So there's an interest in replacing this with laser annealing. First, I'll look at some optical considerations for doing this. If you look at all the different phases of silicon, crystalline silicon shown in the dark purple, and amorphous silicon shown in light purple, and then various states of nanocrystalline and polycrystalline silicon in between. The absorption depth for all these different phases is constant at a wavelength of 355 nanometers, which just so happens to be a common laser wavelength. But this absorption depth is around 10 nanometers. So this would mean that amorphous silicon films in the 10 to 30 nanometer range are ideal for using laser annealing for this. And why you want the absorption depth to be constant is because you don't want your absorption to change as you crystallize the film. Otherwise, you might have to adjust your power. And this just makes sure that you're processing the film uniformly. I also looked at some laser simulation results using a program called LCP Sim. This is a MATLAB program for simulation of laser heat transport and phase change. that was developed at Fraunhofer Institute for Solar Energy. You can see the depth into silicon from the front surface and the temperature as a function of the laser fluence. As the fluence increases, the temperature at the surface increases, but also the gradient of temperature between the front surface and further into the bulk. So we see if we want to be in that 875 degrees C range, we want laser fluences between 0.3 and 0.4 joules per centimeter squared. Here's a quick video of the laser annealing of the polysilicon. It's difficult to see, but there is a color shift as the laser passes over. You may not be able to pick it up with zoom, but it's there. So quickly, I'll discuss the crystallinity. So you can use Raman to detect changes in crystallinity. So amorphous silicon will have a broad low peak, which is because there's a large distribution of bond lengths, whereas polycrystalline silicon will have a narrow, large peak, which is because it has a high number of similar length bonds. So you can see here as the laser fluences increase from the as deposited state, the silicon peak becomes sharper and narrower, indicating increased crystallinity, and it reaches a comparable crystallinity, a Raman signal to the furnace annealed result. I also looked at dopant activation via Hall effect measurement. So the dopants are present in the film, but until they are activated, you can't really measure their change in conductivity or their impact on the conductivity of the film. So this just shows that from the as deposited state with increasing laser fluence, the dopant concentration or dopant activation goes up and reaches a similar value to the furnace annealing. And the resistivity of the film decreases and also reaches a similar value to the furnace annealing. I also optimized the laser for improved passivation and reduced resistivity. This is with a thinner 12 nanometer film using ultraviolet laser processing. You can see that the resistivity decreases with an increase in laser fluence until a certain point it begins to climb back up. And then also there's an optimal fluence for passivation, which occurs roughly at 0.34 joules per centimeter squared. And that agrees with the simulation results. I then take this 0.34 joule per centimeter squared fluence and tune the pulse overlap. What I mean by this, you can see in the bottom right, 0%, the pulses are just touching. 50%, there's a 50% overlap in the pulses, and 75%, there's much more overlap between the pulses. You can see that as the pulse overlap increases, the resistivity continues to decrease. However, there's still a peak in the passivation at around 50% pulse overlap. So that was selected as the optimum. Real quickly, as a table of results, you can see from the as deposited state, the number of dopants is around 10 to the 16. Furnace annealing brings it up to 10 to the 19, and laser brings it up to 10 to the 18. And then also, if you look at the IVOC, the starting value is around 680 millivolts. It goes up to 720 with furnace annealing and 703 with laser processing. But if we use a subsequent silicon nitride layer on top of this, we can bring that IVOC all the way up to 718 millivolts, which is quite comparable with the furnace annealed result. So some products of this work, we have two publications, one at the Photovoltaic Specialist Conference and another which was just published in the IEEE Journal of Photovoltaics. It also led to a project fully funded by the NSF. In the next chapter, I'll discuss laser annealing of Carrier-Selective molybdenum oxide and titanium oxide layers for silicon solar cells. So the key findings of this was that there was improved passivation of the molybdenum oxide with laser annealing, but the laser annealing techniques so far seems inadequate for evaporated titanium dioxide. And then ALD deposited aluminum oxide sees a very strong passivation enhancement across a wide range of laser annealing fluences and repeated scans. So how this works is the beam's just going to pass over these layers in a defocused way. So why use these metal oxides? So currently heterojunction cells are the highest efficiency silicon solar cells at 26.7% efficiency. Again, these work by the intrinsic amorphous silicon providing exceptional passivation, while the N and P amorphous silicon provide the Carrier-Selectivity. However, the issue with amorphous silicon is that it has a roughly 1.8 EV band gap, and this leads to parasitic light absorption that the absorber will never receive. So you have a loss of photocurrent. The dopants in the N and P amorphous silicons can diffuse with temperature into the bulk or into the intrinsic layers, and this can cause recombination. Also, to deposit these layers, you need plasma-enhanced chemical vapor deposition, which is a pretty costly process and uses dangerous, toxic, flammable, and explosive gases. Also, this device can't withstand high temperatures, typically above 250 C, or the amorphous films will begin to crystallize, which actually harms the device. In contrast, metal oxides have much wider band gaps, so there's no parasitic light absorption. They're dopant-free. They obtain their Carrier-Selectivity again by their band alignment. You can deposit them with relatively low-cost techniques like sol gel or thermal evaporation. And metal oxides typically have a much higher melting and crystallization temperature, so you probably don't have to be as careful with temperature, at least hopefully. Again, just the band alignment of how a device using both of these would work. On the one side, you'd have the molybdenum oxide, which would allow holes to tunnel through to the contact and repel electrons away. On the other side, you'd have the TiO2 electron selective layer, which would block holes from reaching that metal, but allow electrons to easily go down to the metal contact. So quickly, there's a lot of info here, but I'll try to get through it. So how we deposited the layers was from molybdenum oxide and titanium oxide. We used stoichiometric pellets and deposited them via thermal evaporation at a low rate of around 0.1 to 0.2 angstroms per second for a final film thickness of 10 nanometers. We also looked at aluminum oxide deposited via atomic layer deposition, and this used a TD mat precursor at 200 degrees Celsius with an oxygen plasma. This results in a rate of 1.2 angstroms per cycle, and the final thickness was easily tunable by adjusting the cycle count, and I used thicknesses between 1.2 and 10 nanometers. So for the molybdenum oxide, furnace annealing just reduces the passivation. Really, any temperature above 100 degrees Celsius totally reduces its passivating ability. But you still need a method to control the stoichiometry and band alignment of this layer. So hopefully laser annealing can help with that. For TiO2 furnace annealing, the passivation is improved from 200 to 300 degrees Celsius. And this is because it reduces the sheet resistance and improves the transmission of the TiO2. But the issue is this temperature is much higher than the molybdenum oxide could handle. For aluminum oxide, furnace annealing improves it. Typically, this is done at 400 degrees Celsius. And this is because it improves the field effect passivation of this layer and the interface properties of the aluminum oxide. However, that 400 degree anneal is much higher temperature than both the TiOX and molybdenum oxide need. So hopefully laser annealing can help with that as well. So for this, I'll use a defocused laser annealing method. The beam is defocused above the sample. And this, again, spreads out the Gaussian peak to have a more uniform processing. And the beam will be raster scanned across these films to anneal them. So first I'll discuss thermal annealing of molybdenum oxide. Annealing improves the transmission up to around 300 degrees Celsius, and then it begins to decrease again. And unfortunately, any temperature above 100 or even at 100 degrees Celsius drastically decreases the lifetime IVOC and recombination current density, or increases the recombination current density of the film. So it has a major detrimental impact even at very low temperatures. Thermal annealing of the titanium oxide. Again, annealing improves its transmission, but this time it goes all the way up to 400 degrees Celsius, where it then begins to decrease again at 500 degrees Celsius. However, annealing up to 200 degrees Celsius seems to have a large improvement on the passivation from the as deposited state, resulting in high IVOCs of 660 millivolts. But at higher temperatures, this effect begins to dampen or drop off, and this is possibly due to crystallization of the film, which is actually not good in this case. Then I looked at laser annealing of the molybdenum oxide, and there's actually a large laser fluence window, which will improve the passivation of the device, improve the lifetime, and decrease the recombination current density. So that's good. This results in a 21% relative increase in the lifetime. Not much impact on the IVOC, but a reduction of 38% relative in the recombination current density, which is good. Unfortunately, for laser annealing of TiO2, of the thermally evaporated TiO2 across a wide range of fluences, even beyond the melting fluence of silicon, it has a negative impact on the device performance. This is believed to be mostly because amorphous TiO2 has a large 355 nanometer absorption, which may cause TiO2 ablation before heating of the silicon TiO2 interface. So hopefully we can use a different wavelength to improve this here, but the current laser system doesn't seem to work with the thermally evaporated TiO2. Lastly, I looked at the ALD deposited aluminum oxide and some thermal annealing first. You can see for a 10 nanometer symmetric structure of aluminum oxide, the lifetime improves substantially to 600 microseconds and the IVOC up to 673 millivolts. If we use a thinner film of 1.2 nanometers in a higher temperature, again, we can get a 627 microsecond lifetime and a 666 millivolt IVOC, which is quite good. We can then deposit the TiO2 and molybdenum oxide layers on either side. And doing so, that would be a full Carrier-Selective device. We get an IVOC of 668 millivolts and a tau fit, a lifetime of 583 microseconds. Lastly, one thing I looked at is if you leave the native oxide intact and deposit a very thin aluminum oxide on top, and then do a furnace anneal, you can get a lifetime nearing 1 millisecond and a very high IVOC of 687 millivolts. So that's a very easy way to passivate. Also, I looked at laser annealing of the aluminum oxide, and this results in a remarkable improvement in the passivation across a wide range of laser fluences that I tested, and also a number of repeated laser scans. So you can see the implied open circuit voltage increasing with laser fluence. And if we take this maximum fluence and repeat that across up to 100 scans, the IVOC continues to increase up to 630 millivolts from a starting value of around 545. So some products of this work, there's one publication so far on that was published in the Photovoltaic Specialist Conference this year. Part of this work was also fully funded by the NSF. And we were also selected for a joint study with the Center for Nanophase Materials at Oak Ridge National Lab for this work. Now I'll change gears a little bit and talk about the impact of pulse laser heating on silicon passivation and defect generation. So the key findings of this work were that I studied the impact of varied laser fluence and process area percentage on the generation of defects and also the impact on passivation. I tried to provide a fundamental understanding of the laser-induced defects in well-passivated silicon, and then identified the power range to minimize defect generation, but still ensure film modification. And then lastly, I characterized these laser-induced defects. So what am I talking about here? If you have a well-passivated silicon sample, with one of the best ways to do this is with aluminum oxide and silicon nitride. And doing this, I obtained a lifetime of 2.5 milliseconds, which is very high, and a 721 millivolt IVOC. You can then take the laser and process a small area, percentage area of the device at increasing laser fluences and see if this leads to any defect or dislocation generation in the silicon lattice. These defects will cause increased recombination sites within the bandgap, which will hurt your device performance. So first, I looked at laser processed square areas. These square areas are similar to a laser annealing approach. And I looked at 1% of the area, 5% of the area, and 10% of the area with a 0% pulse overlap. And then I just did 1% at increasing laser fluences, and then 5% at increasing laser fluences, and then 10% at increasing laser fluences. You can see the impact on the passivation in the other squares there. You can see initially for fluences less than 1 joule per centimeter squared, they have the largest impact on the initial drop in the passivation. And above this fluence, the damage is basically already done, and the passivation doesn't decrease much further. It sort of saturates. But every time you increase the area from 1 to 5%, there's an additional further degradation in the passivation. And with higher fluences, it follows a similar trend. Additionally, I looked at laser processed lines. This is more similar to dielectric opening used for finger contact deposition. You need to ablate your dielectric to deposit fingered contacts. Again, the pulse overlap is 0%, and what I did was I just drew lines across the entire sample. For 1%, for a 25 millimeter wafer, it's roughly 5 lines with the 4 millimeter spacing, 5%, 25 lines, and 10%, 50 lines, with, of course, the spacing between lines decreasing. So again, increasing the laser processed area results in the largest drop in passivation. The diffusion length of carriers in silicon is roughly 100 to 300 microns, and that's on the order of the line spacing. So there's plenty of recombination sites for the silicon, or for the carriers to recombine here. Fluences above the 0.25 joule per centimeter squared fluence have similar impact. They all kind of decrease at the same amount. But 0.25 still has a substantial impact, but the damage is minimized there. So what is exactly happening to this sample? I looked at optical microscopy first. You can see at very low fluences, there's no damage to the passivation layers. And then at 0.25, there begins to be some swelling of the film and partial ablation. And then at 0.42 joules per centimeter squared, there is a significant ablation, and you can see the silicon absorber underneath. And if you continue to increase the fluence, it results in larger and larger damage spot, and also increased silicon melting and damage to the silicon. In the bottom right here, you can see the spot size. This is at the full laser fluence, was roughly 51 microns. And for this study, the same area was processed at the increasing laser fluences. So that's sort of why you see multiple spots in these areas. I also looked at white light interferometry. So this is ZIGO. It's just an optical profiling technique. You can see that as the laser fluence increases, you can see more and more damage and more melt depth in the sample. And then I have the highest fluence reconstructed here on the right in 3D. So you can see sort of the craters that are formed by the laser pulse. In the bottom right here, you can look at sort of the damage depth as a function of the laser fluence. And you can see that it first rapidly increases, and then it sort of increases linearly with increasing laser fluence. I looked at microphotoluminescence to look at the effect of passivation and also on the defects. To do this, I used a 400 nanometer wavelength to make sure the signal came mostly from the silicon surface. And also the beam size was focused to roughly less than 1 millimeter squared, so that it could be contained in those square areas I was mentioning earlier. You can see that there's an exponential loss in the localized photoluminescence signal just inside that square area. As the laser fluence increases linearly, you can see this is in log scale, and the passivation is decreasing exponentially. You can also look at this for defect peaks. There are 4 defect peaks that appear in photoluminescence: the D1, D2, D3, and D4 peak, which correspond to dislocations in the silicon lattice. You can see that at 1.27, the D1 peak begins to appear, and then the D2 and D3 peak appear at higher fluences of 3.45 joules per centimeter squared. And then at even higher fluences, these peaks all disappear, possibly due to remelting of the silicon in the laser processed area. Unfortunately, I couldn't see the D4 peak because it was hidden by the band-to-band peak. It would typically be located somewhere here, but that was shadowed. Yeah. I also looked at Raman and amorphous silicon generation. Again, for Raman, a narrow sharp peak indicates more crystalline silicon, while a broad shallow peak indicates amorphous silicon. You can see that as the laser fluence increases, the peak height drops substantially, and it also broadens. But then at a certain fluence, it begins to get sharper again, or at least increase in intensity. And this is possibly due to a recrystallization of the silicon at high laser fluences. These are not normalized to each other. I just showed the raw Raman signal. But what you can do is you can take the full width half maximum of each of these peaks and plot it versus the laser fluence. And you can use this as a measure of the structural distribution. So a larger full width half max means that your silicon is less crystalline. And you can see here as the laser fluence increases, at first there's a large increase in the full width half max, but then it begins to level off at higher fluences. So some products of this work: I've identified the laser power regime for nanosecond pulsed ultraviolet lasers to minimize defects for pattern dielectric removal and annealing. And I'm also working on a manuscript for this study with the aim of submitting it for journal publication. In the final chapter, I'll discuss a laser direct wafer bonding for solar cell junction formation. My key findings of this work were that I address all the optical challenges involved in this task. I experimentally demonstrate the laser direct wafer bonding process, and I obtain a photovoltaic response from illuminated and passivated PN bonded wafers. So what is wafer bonding? For furnace wafer bonding, there's 2 typical ways you do it. There's hydrophobic bonding, in which 2 wafers are placed together without water, and the van der Waals interactions bring wafers together. And then with heightened temperature, typically around 1100 degrees Celsius, silicon-silicon bonds are generated and the 2 wafers are bonded. This requires some pressure and high temperatures. There's also hydrophilic bonding, which uses water at the interface between the 2 wafers. So you would place water between the 2 wafers, and then you have hydrogen bonds form. And then you'll form with 800 degrees Celsius temperatures, roughly, silicon, oxygen, silicon bonds. This also bonds the wafers, and typically results in higher bonding energies at lower temperatures. Also, we can look at techniques for laser and volume marking and even wafer bonding. So on the left, you can see Kramer et al. Used in volume marking with the 1550 nanometer ultrafast laser. This technique relied sort of on 2-photon absorption to generate these cavities in the bulk in silicon. Shambanu et al. Used a 1550 nanometer laser and ultrafast laser to generate waveguides within silicon. And you can see the different waveguides generated in the volume at different laser fluences. And the last guy, Wissinger et al. Used a 1940 nanometer laser with an absorbing interlayer to bond 2 wafers together. This results in quite a nice bond, but the issue with using the absorbing layer is that you would not be able to get any good p-n junction performance across the 2 wafers. So how I plan to do this is to use an n-doped wafer and a p-plus doped wafer. They'll be cleaned, and then DI water will be placed between them, and they'll be stacked. Or how I did this, and then a 1064 nanometer laser with a 50 nanosecond pulse is focused through a 0.55 NA aspheric lens, which is focused to the interface between the 2 wafers where laser bonded spots are generated for laser transmission bonding. And then lastly, I'll just test the p-n junction performance to see if a p-n junction is formed. So some optical considerations for this. You can see that the absorption depth, the main one is the absorption depth of silicon in green. It doesn't exceed the typical wafer thickness until the wavelength's above 1 micron. So this means that if you're using lasers with wavelengths below 1 micron, your laser light will never really reach the interface between the 2 wafers. So those won't work well. However, if you go too far beyond, again, you're reaching crazy absorption depths. You'll never really have light absorption. So you want to be in this sort of sweet spot here between 1000 and 1150 nanometers. Also, there will be some reflection loss from the front wafer. Reflection shown in red, roughly 30% at 1060 in that range. And you also have some absorption losses. One thing I exploited was free carrier absorption. This is typically thought of as a parasitic process for solar cells. It's an intraband absorption process where with highly doped semiconductors, an electron already in the conduction band can absorb more light and transfer to a different position in the conduction band. So you don't get any photocarrier generation, but the optical energy is lost. How this works is it basically increases the near-infrared absorption depth roughly an order of magnitude for every order of magnitude you increase the dopant concentration. So this can be, and compared to the undoped silicon, you can see that the absorption increases a pretty, an order of magnitude with every order of magnitude of the dopant concentration. So this is useful for laser absorption of light in the bottom wafer. So you can heavily dope your bottom wafer, and it'll drastically improve the absorption depth. So for example, at 1064 nanometers, the absorption depth in undoped silicon is roughly 900 microns. But if you look down to 10 to the 20 doped, boron doped silicon, the absorption depth is 25 microns. So you absorb that light much more close to the surface. So then if you factor in the relative absorption, the top wafer, if your top wafer is 280 microns thick, you'll absorb 24% of the relative intensity in the top wafer, whereas the bottom wafer, which is heavily doped, will absorb 99% of the remaining light intensity in the first 120 microns from its surface. So the absorption depth is the absorption is much stronger with the heavily doped wafer. You also want to look at the half angular aperture and refractive index. So as you increase your lens numerical aperture, you increase your half angular aperture, which is useful for getting a tight depth of focus and really just injecting the energy where you'd like to. However, this effect is lessened because you have to focus through silicon, which has a high refractive index, and it'll reduce your half angular aperture pretty substantially. However, it's still necessary to use these high NA aspheric lenses because you want to reduce your spherical aberration as much as possible. And you also want to prevent any damage to your front surfaces or the bulk of the top wafer as much as possible. So you actually have, because of the refractive index change in the silicon, you'll have a shift in your focal length. If you just focused at the front surface, you might expect a profile like this. But then if you shift your wafer up by the thickness of the wafer, the light will actually be bent due to Snell's law through the wafer and focus behind it. So this won't work. You can just use some clever trigonometry and you'll find a height that you need to move the wafer up to get the light to focus exactly at the rear surface. So I did that and I parameterized it in terms of a few different things. One is the focal shift. This number isn't important really overall. It's just helpful it's not really helpful when considered alone, but it's helpful to know where to move your Z stage. And I did this for a variety of different wafer thicknesses and lens numerical apertures. What's more important is the difference between the focal height at the front of the surface and the rear surface of the wafer. If this number is too small and your depth of focus is not large enough, you may end up just marking the front surface without marking the rear surface at all. So you want a large difference here to prevent front surface marking. And then this last thing is the beam diameter. You want a substantially large beam diameter at the front. Again, because you're going to lose 24% of your light through the top wafer. You want to make sure your beam is nice and large so that it doesn't cause any melting at the front surface. So yeah. So here's my experimental setup for this. These are infrared images taken. So the 1064 nanometer laser light comes down. It gets focused by a high numerical aperture aspheric lens, and it's focused to the interface between two stacked silicon wafers. The two wafers are kept level by a kinematic stage, which is necessary because the depth of focus is roughly 10 to 15 microns using this lens. And this whole setup is sort of translated by a motorized XY stage under the beam. And on the right, you can see sort of a close-up of the infrared light going through that high NA lens and being focused through the front wafer to the interface between the two. Quickly, some IV results of just the non-bonded wafers. So if you just take the N wafer and measure the IV from front to back, it's relatively resistive because it's got a low doping concentration. If you look at the P plus wafer, it's got a little bit more conductive profile because of its high doping content. And then if you just stack the two wafers on top of each other without doing any bonding, you can measure diode performance, but it's more of a Schottky diode due to its low knee voltage. You can also measure the stacked wafers under dark and light illuminated IV. This is at 1 sun, and you can see there's a slight increase in the photocurrent. But again, the knee voltage is low. It's more of a Schottky diode than it is PN diode. So there's a little bit of photovoltaic response. So that's good. I also looked at Zygo to see the profile of the interface marks. So these are marks, what's shown here is the front surface of the bottom wafer. So these are marks that were generated at the interface between the two. And the front surface of the top wafer was completely unmarked. So you can see the profile. I did this for both the rear of the top wafer and the front of the bottom wafer. The rear of the top had peak heights of 70 to 110 nanometers, whereas the front of the bottom wafer had them between 30 and 90 nanometers. So we need an interwafer spacing of roughly 100 to 200 nanometer spacing, or 200 nanometers for this to work well. Lastly, you can see two bonded wafers here on the left. I did this with the process described beforehand. I'm holding just the rear wafer there, and you can see that the front wafer remains attached to the rear wafer. So you can see there's two perfectly bonded wafers. They're still attached today. They haven't come apart. And I also, after I made this, I deposited indium contacts on it and measured the IV performance. And you can see that this is under illumination. I get a photovoltaic curve, and it's got a nice VOC of 652 millivolts, which indicates a PN junction formation. However, the current is still relatively low for a variety of reasons. One, there's a very high series resistance of 700 ohms. So hopefully further bonding could improve that. Also, there's no anti-reflection coating deposited, so I'm losing roughly 30% of the light from reflecting off the front surface. There's also lots of light absorption in that top wafer. So it's not, a lot of the light and the carriers won't reach the interface. Additionally, if you just consider how I did the bonding, there's only 0.648 centimeters squared of bonded area. So not the full 25 by 25 millimeters is bonded. So some products of this work, I've developed a laser method for wafer bonding that remains at low temperature and enables PN diode performance. And I've also got working on a manuscript with the aim of submitting it for journal publication. So the accomplishments of this work, the primary goal of this work was to increase the efficiency while reducing the manufacturing costs of carrier-selected contacted photovoltaic devices, provide a fundamental understanding of the laser-generated defects, and demonstrate a novel laser direct wafer bonding process. In this aim, I've demonstrated the electron transporting layer in perovskite solar cells can be laser annealed to allow the use of flexible substrates and efficiencies of 17.1% on those substrates. I've demonstrated a laser annealing allows for the fabrication of state-of-the-art TOPCon silicon solar cells at relatively lower temperatures, under 500 degrees Celsius, which enabled 718 millivolt IVOCs. I've provided a systematic evaluation for the understanding of laser-generated defects and their impact on device passivation, with the identification of a power regime for minimization of defects. And I've demonstrated a PN junction device by laser bonding of 2 wafers, which eliminates the need for high temperature processing and also eliminates any dope and diffusion processes. There's a list of publications. I've got 6 so far, with 2 more expected one on the impact of laser annealing on passivation and defects, and one on the direct wafer laser bonding. List of conference presentations, roughly 6 so far. 1 more is in the works this January. And then a list of awards, funding, and other notable activities, which I'll just skip over in the interest of time. Thank you. That's all I've got. Does anyone have any questions?
Thank you, George. Great talk.
Thank you.
Do we have any questions from the audience?
You may need to unmute yourself if you want to ask.
Sure, I've got one question. George, nice job. It was great.
Thanks, Jeremy.
With regards to the sphere collaboration from the microscope objective on that last project,
Yeah.
So the A-sphere was designed to minimize sphere collaboration, I assume, in air.
Right.
Okay. So did you observe, I mean, it's a thin wafer, but did you observe any induced sphere collaboration when you were focusing on the back surface of the substrate?
So unfortunately, I didn't get to profile the full depth of the damage. I imagine there's going to be a lot of sphere collaboration because of the silicon. But the best we could really do was with the A-sphere that I had.
Yeah.
But yeah, a TEM study to see if there's any further damage in the silicon, the top silicon wafer would be helpful. I agree. Yeah, that's something to look into. Yeah, there's definitely sphere collaboration within the silicon, but it's hard to quantify that. I didn't look at that yet, but that would happen.
All right, cool. Thanks.
Sure.
Any other questions from the audience? George, do you need a break before we start with the committee questions, or?
I don't think so. I'll just get water, I think, real quick. And
That's fine with me.
yeah, I think I'm ready.
Okay. Okay, so Josh, do you want to start with your questions?
Sure, I can do that.
Okay.
Hi, George. Nice work.
Thank you.
All right, so I guess I have a few questions. Okay, well, first one was slide 26. It was some MATLAB simulation of heat transfer and then temperature, I guess, as a function of depth.
This one?
Yeah.
Yeah.
So I thought that this pulse laser annealing, the advantage is that you get very localized increase in heating at the temperature. So, and then the way I read this plot here, as a function of fluence, you can get quite a high temperature quite deep into the material. So what does this assume? Does this assume some sort of a steady state temperature profile when you just keep on shooting the laser to the silicon? So how does this silicon for hundreds of nanometer reach, let's say above 800 Celsius degree under this laser condition? Is this what really happens to your material, or is this some sort of some assumption that that goes into the simulation?
So it is a bit idealized. Another issue with this is it has difficulty taking very small steps. I can set it to small, 10 nanometer steps, but based on how it works, it'll just automatically increase the step width. I didn't write this code. It does have the change in, refractive index and extinction coefficient with temperature for silicon for pretty much all temperatures up to the ablation temperature. So it basically stepwise calculates the temperature, then evaluates if the pulse is still there, how much is reflected from there, how much is absorbed, and then recalculates how much temperature it increases. And then from there, it'll just how the heat diffuses. I think I took this at this is all taken, so this is at a certain time, obviously. This might be after like 50 nanoseconds with a 25 nanosecond pulse. So there is some heat diffusion with time. I can't recall exactly when I called the time on this to stop. I don't believe it was at the height of the pulse. But yes, there is some heat diffusion. This is just for crystalline silicon. A lot of what I'm doing is these thin layers on the surface there, or amorphous silicon or polysilicon. The temperature diffusion in those is much lower. I don't have the numbers in front of me, but it's something like 0.9 for crystalline silicon, centimeters, or I forget the unit Kelvin, centimeter Kelvin per, I forget exactly what the units are for that. But amorphous silicon and polysilicon are like in the 0.1 range. So 9 times less.
Okay. So it will be also a function of what wavelength you use, and then the, I guess, the extinction coefficient at that wavelength of the so. Right. If the material absorbed the wavelength much stronger, then I guess this profile will be much sharper toward the front, right?
Right. This was at 355. I know this program works well for 532 and 1064. I believe the 355 worked well, but I don't think Fraunhofer measured this UV absorption with temperature. I think it's taken from someone else. So there could be other things happening, but yeah, I just took it as a general guide just to sort of get me in the right range for the surface. I don't know how much temperature is actually diffusing in my sample.
All right, thank you. I had some other question I had was, if you go to slide 28, I think it was 28. No, I'm sorry. If you keep going, there is a table of performance here. So you got the much better result after depositing silicon nitride. Mm-hmm. What does silicon nitride layer do?
So it'll improve passivation. It also at this thickness, I use a 60 nanometer film. It'll act as an anti-reflection coating a bit, so that'll allow for more light capture.
But it seems to improve the passivation as well, even though you're depositing silicon nitride on the most outside layer.
Right. It'll also it has a field effect passivation, I believe silicon nitride does, and this can further improve band bending within the full thing.
So it provides some sort of a charged layer which repels the carrier.
Yeah, so that also helps there. I just did this sort of at the end. I didn't sort of characterize what exactly is happening with that one, but I can look into that some more. Slide 31. What exactly the silicon nitride does to the passivation. Okay.
Yeah, but this work definitely shows promise of laser processing. Yeah. And then cool, thank you. And then another question I had was, when you do wafer bonding, so I guess ideally it would be nice if you could just have localized heating right at the interface between the two wafer, right? Mm-hmm. And so instead of hitting the top layer, I'm trying to understand the rationale behind the wavelength you selected, and you showed as a function of depth what the absorption might be, things like that. And I guess you selected the wavelength just right at the onset of the absorption of the silicon, so that you get to have absorption somewhat deeper into the, I guess, beyond the first wafer. Was that the rationale?
Right. So there's the absorption depth at 1064 for undoped silicon is roughly 900 micron. Your typical wafer being, between, maybe 180 and 300 nanometers thick or microns thick. So hopefully enough light can reach the interface, but the absorption is still, strong enough that you can absorb the light while using nanosecond pulses. The other techniques here rely on, ultra fast lasers and 2-photon absorption, whereas I'm relying on a nanosecond laser, so I can't exploit this property as easily.
Yeah, I don't think your pulse, the nanosecond pulse, will cause much of a nonlinear
No, it won't.
effect of a mixing of a photon or something like that. But
Right.
I guess what I'm trying to understand is like the process through which you're hitting, localized hitting around the interface that you hope for is occurring. So this is not, you mentioned briefly some intraband absorption of the electrons if you use wavelength in the near infrared, right?
Yeah.
But this is but the experiment you did is not that process, right? It is interband transition that you're causing, right? Is it? With
Well,
1,000.
So this is basically just an increase in the absorption depth with the doping. When I'm doing my structure, where is it? So I'm using a P+ wafer. This is doped 10 to the 20 on the bottom. So I am getting that absorption depth, that's roughly 25 microns with the bottom wafer. So the difference between the top and bottom, the absorption depth at 1064 is 925.
Also, you are using intraband absorption on the heavily doped bottom.
Right.
Wafer. So you're pretty much, but then even then the penetration of laser would be quite deep into the even second wafer, right?
That's true. So then what I'm also relying on is the high, with the high NA lens, that the focus is nice and tight, right where I want it to be. Yeah.
Okay.
I mean,
okay, so you're trying to focus onto the interface about as much as you can, but you would probably have a quite large heat load onto the bottom wafer.
Right. Yeah, it'd be nice to do some TEM on this and see sort of if there is melting or change in crystal structure in either wafer with this. But so far these things have remained bonded, so I'd have to snap them apart to do this. But yeah. So I'm also relying on the high half-angle aperture, with these high NA lenses. So hopefully that the focus is real tight and the spot size is real tight at the interface. But yeah.
Yeah. Yeah, I see it. That's why now I understand why people might put like absorption layer, but then there will be a lot of contamination and not a good interface formation.
Right.
Okay. And you said you put water there. What was the reason for water?
So with the furnace bonding, water sort of typically helps with lower temperature bonding between the two wafers, and also just the bonding energy is typically higher at those lower temperatures with water bonding. So I was trying this initially without any water, and occasionally I'd get them to stick for a bit, but then they'd fall off. So that, I don't even know if it was really bonded or just sort of a van der Waals force holding them together. But after I just tried water one time after checking out a paper, and they immediately stuck together. So I was like, well, that works pretty well. And then most of it was just testing IV. This could also probably result in some of the series loss shown in that last IV curve. Series loss, and also fill factor loss. There could be SiO, Si bonds.
So if people use, let's say, nonlinear optics with the let's say femtosecond laser system, the 2-photon absorption or some sort of photon mixing, so you get really localized heating, do they get much better bonding and performance if they did all of that?
So I've never seen bonding with the 2-photon absorption. At least I wasn't able to find anything on that. Most of people have just done sort of, creating cavities or waveguides or things for microfluidics. The only guy who did the bonding he's the absorbing layer, and this 940 nanometer laser, I believe this was also picosecond. This 940 nanometer wavelength is, super transparent to silicon, so he's not relying on any 2-photon process. But
yeah, the ultra fast laser system would be quite expensive.
Yeah.
Yeah, I think if your approach is successful, that probably would be a
I
lot
think
more.
it could work. Yeah, we just don't have the tool. That would be fun to explore.
Yeah. Okay. So I guess bigger picture question is so what in the solar cell industry, is there any has a laser processing been incorporated in a so far in a meaningful way in any of the commercial systems, commercial products?
Yeah, it's used for wafer dicing for sure. Commercially, they use 1064 nanosecond lasers for that. Although I think they're shifting to more picosecond now. They also use laser using ultraviolet lasers like I've used, but more picosecond lasers for dielectric opening. Like in this study, you'd open your dielectric here and then deposit your metal fingers for the subsequent device. But annealing, I wouldn't say it's common at all industrially yet.
Is it what do you think the cause of that is? Because it could be a lot more economical, right, with the less heat load, and I don't know how the throughput issues might be, reliability, or so. What do you think is the key to getting this laser processing into the let's say production line for solar cells?
I think, well, one issue is, they've got this, the thermal process is sort of down to a science now. I believe they spend it's something like 1 to 2 seconds per process for a wafer. So you need to make sure whatever laser process you incorporate is as fast or faster than that. And also, a lot of these furnaces, they can process bulk wafers or multiple wafers at a time. Whereas, of course, one laser can really only address one sample at a time. It can do it quickly, but if you have hundreds of wafers going through, there's issues with that. You can always get more lasers, but that becomes expensive. I guess I didn't look too much at what's the barriers to industrial adoption, but I think as you get higher and higher power lasers, which is becoming, they're sort of diode laser efficiencies are increasing, or diode laser powers are increasing sort of with Moore's law. As those get cheaper and more efficient, you'll begin to see more adoption of those in the industry, and any industry really. But, yeah.
All right. Yeah, thank you. So that's some of the questions I have. I guess I will pass on to the other committee members. Thank you, George.
Sure, thank you.
Okay. John, do you want to go next?
Sure. Thanks, George. That was a nice presentation. I enjoyed that.
Thank you.
I have a question. I have several questions. I'm going to start with something kind of technological, and then I'm going to go into some more fundamental things. On slide 20, you did a comparison of some different solar cells. One was on a rigid substrate, one was on a flexible substrate, and you had some different values. Yeah. So I'm curious. So it looks like you did the same process for the device on the left as the one on the right, but you got different VOCs and currents. And can you maybe hypothesize as to why things weren't the same?
So I actually did use a different anode material for the flexible device. I used gold for this result instead of silver for these two. So there is a difference there, and that might affect the VOC with work function offset with the whole transporting line. As for the higher current, it's possible that the substrate is different. And these devices, even though I show it like this, the substrate, when I measure it, is actually on top towards the light. So the light passes through the substrate first, and then to the wafer, and then to the perovskite. So there could be differences there in light absorption. The flexible substrate was much thinner than the glass, obviously. And I think the ITO was slightly different as well, even though they came from the same vendor. That's my best guess.
Okay, yeah, so it wasn't a total apples to apples comparison.
No, it's not.
Yeah, it's interesting to me that the performance was identical.
Yeah, same PCE, but yeah, different fill factors and different current and voltage. Yeah.
Okay, cool. One statement you just made, which is something that I noticed in the write-up and in your presentation as well. You mentioned work function,
Mhm.
and you use work function a lot to try to tune device properties. So, for example, the metal oxides, the transition metal oxide you're using. Can you explain to me why they have different work functions?
Why they have different work functions. So it's sort of like here I have a slide, I think, at the end. Those different. Yeah, so sort of all the different dielectrics and electron selective and Hall selective layers I looked at. So sort of what I'm describing as a work function is a difference between the vacuum level and the conduction band of them. Why they have different levels? I guess it's a good question. I wasn't prepared for this one really. Forget the equation for work function. I apologize.
Do you know what the work function means? You kind of said it.
The difference between the vacuum level energy and the conduction level, or the Fermi level. Sorry.
So it's the energy to do what?
Move an electron from the vacuum level into the conduction band, basically.
Vice versa. Yeah, the opposite of that, right? Okay. I don't actually know the answer to the question. I just thought I'd ask.
Yeah, I'll definitely, I can add that into the thing. I don't know if I defined it well in the thesis at all. Yeah.
So building on this metal oxide discussion,
Mhm.
I was interested. So you did some experiments. We had molybdenum oxide and titanium oxide, and then you did either furnace annealing or laser annealing.
Mhm.
And the molybdenum oxide really did not perform well with the furnace annealing, I think.
Yeah.
Do you know why? Do you have an explanation for why it didn't work well?
So let's see, where was that?
I think it's 37.
Yeah, so some of the explanations so far I've seen is that so I did this annealing again in air, and then some people think that there's filling of oxygen vacancies, which causes the loss. Really, it's not too well explored for passivation. A few people have theorized why, but a lot of people just kind of agree not to anneal it. Would have been nice to do sort of a more, characterization, understanding of why that's occurring. But yeah, I have to imagine it has to do with changes in stoichiometry or the work function alignment. Again, with sort of how this works, getting this to be right at the edge here to allow holes to tunnel through, but also having the band bending, it's a very precise band alignment that it needs. And I'm thinking the annealing, even at low temperatures, can shift this and basically cause it to, allow electrons through or just allow tons of recombination or other issues.
So what experiment might you do to answer that question as to why it degrades with annealing?
I guess for the work function alignment, we wanted to use electron energy loss spectroscopy. We were going to do that with Oak Ridge, hopefully, so to see how the work function shifts with temperature. We could also use XPS to look at the stoichiometry of the molybdenum to oxygen ratio. Again, molybdenum trioxide is an insulator, which would not be good for carrier-selectivity. It'd just be like a barrier. But molybdenum dioxide is sort of a conductor, so that's also bad. So we want a ratio in between, but I don't know if anyone's really spelled out the optimal, stoichiometry for this type of layer. So we'd look at that. Obviously, we have the method of measuring passivation, but yeah, I think hopefully that would help. And we could use, I guess we want to look at defects. You could use capacitance voltage measurements across the film as well. But yeah.
Yeah. All right, cool. And then I think you said that the TiO2 did not do well with laser annealing. Is that?
Yeah, unfortunately, we explored this a few times. And there's not even a slight increase at any of these laser powers. It initially, even at very low fluences, began dropping, which is kind of disheartening. I'm not sure
why.
The idea was, so I don't have any chart in front of me, but the absorption of TiO2 in the amorphous state, if you look at it, it begins to shoot up around 360 nanometers, quite high. And the thought is that when it's in this evaporated state, it's very amorphous and it's absorbing way too much UV light, and it's ablating the film before it can even begin to anneal or reach that surface between the silicon and the titanium dioxide.
So what's the band gap of TiO2 in terms of nanometers?
In nanometers, I think it's right around 355. I know they use it for hydrogen fuel cells and things like that to convert UV light into oxygen or hydrogen for hydrogen fuel cells.
Mm-hmm.
But,
okay, so you're just parked right at the band gap, basically.
Right. So one thing we were going to try soon was using a 405 CW diode laser, which still has that, the absorption depth for silicon is, instead of 10 nanometers, it's like 100 nanometers. But we were still getting that set up, before I was defending. So
okay.
The idea with that is hopefully, that band gaps or that wavelength will still allow for the annealing near the surface, but it's not so close to the band gap of the TiO2 that it'll ablate the film.
Okay, I've got two more questions. One more fundamental and then one just a clarification thing. So I'll start with the fundamental one. You use Raman quite a bit.
Mm-hmm.
Can you describe to me how Raman works?
So let's look at a random spectra for this. So Raman, you have a laser wavelength coming into the material, and it's an inelastic scattering technique where the light is absorbed and there's sort of an inelastic scattering with the material. And this re-emits light, either Stokes or anti-Stokes shifts. And then the number of, similar lengths, Raman shifts that you get, they indicate basically the bond length. If they're all at the same point, it means most of your bonds are the same length and you have a narrow distribution. And then if you have a lot of different bond lengths, you get a, very low signal, but a very broad signal. So I just kind of use it as an indicator of crystallinity. That's relatively easy.
So why does bond length affect the inelastic scattering?
So, I mean, so all of these different bond lengths will have a Raman signal, but this is basically like a counting procedure. The intensity is just a counting of the number of bond lengths. So if you have a bunch of them at the same bond length, they'll have Raman signal. The Raman signal at one in particular Raman shift will be much higher. Are you looking for more fundamental?
Yeah, you're right. I just wanted to see if you knew. It's phonons, right?
Right.
So your phonon frequency will change depending on bond length. Cool. All right. And the last thing is just a clarification. On slide 36, you had you showed that you use aluminum oxide by ALD. Was that done here?
Yes.
Okay, then just a clarification. The precursor is not TDMA, it's TMA.
TMA. Oh, my bad.
So if you write a publication on this, just
Okay.
want to get that right.
Yeah, change the precursor. Sorry about that.
Oh, it's no worries. Just want to make sure
I
you do.
remember reading that on the system or something. Yeah. Okay. Make sure I fix that.
Okay, that's all I got. Thanks.
Sure. Thanks, Professor Ivo.
Kisong?
Can you hear me?
Yes, I can hear you now.
Okay, so I have a few questions. So first about your bonding method. So
Okay.
I think it's very, very interesting. So it's very, very simple few questions. So you do the direct bonding of the silicon by silicon to use the those laser like the method. So I was curious. So there's a lot of interest to do those bonding to form the kind of the electrically like the active interface using the some oxide material as well. So I'm wondering, but in real case, they care about those interface thickness to perform the reasonably high performance PN junction or some electrical junction. So have you analyzed the interface between the two wafer? So have you take a look at the cross-sectional TEM or the SEM, how the interface looks like? What is the thickness at those interface layer, is for example, the oxide layer, and then how uniformly it is distributed in the kind of retro resolution?
I have not, unfortunately. That would definitely be the next part in this, because we have the bond. I just kind of want to see what's going on. But no, I didn't have time to do any TEM.
I see. And the other question is that usually when you do the kind of the annealing bonding at high temperature using those water drums, they sometimes apply some pressure to kind of keep the interface
Right.
squeezed. So have you done that, or you just directly placed it and then just annealed it?
So because I used the water, I did end up applying some pressure, not really pressure, but I just used a small weight on top of the sample to push them the two together. But that's because if I just use the water, they'd be floating. One would be floating on top of the water. So I use it to sort of pull them
Yeah, so one thing I'm kind of curious is that if you kind of apply the water, so you can minimize the interface, like the gap between the two vapors, so that you can, because like those interfacial thickness at the oxide layer might affect a lot of like the electrical junction. So the other question is that this might work for the other material system. Have you ever tried to bond the silicon to the other material, like the for the heterogeneous integration, like gallium arsenide or the other material system?
No, I haven't. I think at our lab we've done some bonding of glass to silicon. I think, I'm not sure, but that's another student's project. I haven't worked on that myself.
I see. So you don't aware of the result of those bonding method?
I haven't done
work well?
So I guess it depends on your, whatever, if material has the, smaller band gap, you'd put on top, basically, so that you could do the bonding. So yeah, I guess you do it upside down for gallium arsenide. If you're going to put it on silicon or something. But
I see.
Depends on your band gap, I guess.
I see. And you showed the other example of those similar bonding method. How do you compare your method versus the conventional, like the water-based those furnace annealing bonding method in terms of like the interfacial characteristic?
So I don't know if I've seen any. I can't say I've looked too much for any, I guess electrical performance of an interface for two wafers bonded this way. But I guess what you'd look at is sort of, series resistance obviously is a big one. If the bond is not good or there's not incomplete, there'll be lower series resistance for the area. One thing to look at the bond strength is obviously the surface energy, but we didn't really have an apparatus for that. At least in our lab, I think on campus or on grounds we do somewhere, but.
I see. So, but yeah, you're aware of that people trying to make the junction using the similar method, vapor bonding, right? So they use for example, the ALD process aluminum oxide, and people got the pretty reasonably good performance for those type of the bonding interface. So yeah, I think this is very, very interesting work, especially to me as well. And then the one more question about the bonding is that you use the focus, right? So if you go to the slide 57 or 58, can you go?
This one?
Oh yeah, like 60. Yeah. So is there any kind of a specific reason to focus it instead of using the culminated beam at the interface? So what is the kind of major purpose of the focusing at the interface?
So if you just use a collimated beam, one issue is you need to induce melting. Because the silicon still has an absorption of 1054 light, even though it's relatively weak. This means from the front surface of the wafer to the rear surface of the wafer, you're going to lose roughly 24% of your beam's initial intensity. So if you want to induce melting and the beam's perfectly collimated, if you get it to a temperature enough that you want to melt the rear surface, it's going to melt the front surface before even getting to the rear surface.
I see.
Yeah.
But if you focus it, but the bonding interface will be localized, so it will not bond everywhere. Isn't that true? Or
right, it is. So it's just basically just through raster lines of bonding for this technique. I guess one idea is, I think you have to do that because you have to keep it focused for this, unless, I guess if you had a high enough doped wafer and a low enough doped on the front, maybe it could work. But I tried this without the high NA lens. I tried it with just a Galvo lens, beta lens, and I wasn't having much luck getting the mark.
I see. But that is because the silicon has the absorption tail. So just in case if you use the wide bandgap material like the gallium nitride, do you think you still need to focus it? Or if there's no absorption tail at this 1550, do you think it would work to bond without the focusing?
Yeah, probably. I think it might work. Yeah. You need a significant laser power or fluence to.
Oh, I see. To kind of have the. I see.
Or reduce at least enough temperature.
So, do you think it will melt the interface to make the diffusion-based bonding, or it just kind of activate the surface energy to bond together to oxide interface? What is the kind of the working mechanism?
I don't think
in your case, yeah.
In my case, I definitely had melting, and that resulted in, assisted with the bonding. But obviously, the melting temperature for silicon is 1400 Celsius. So you don't need anywhere near that to get the bonding with these other methods.
I see.
Yeah, you can get the bonds without it, without melting. But for this, for this project, obviously, I'm inducing these lines of melt that are roughly 100 nanometers high. Yeah.
Nice. So when people do those type of direct bonding, they usually kind of activate the surface using the plasma treatment. So have you ever tried those pre-treatment for your case, or is just bare wafer and then you just bonding it?
I cleaned the wafers with HF. I did actually for this device. I forgot to mention I used aluminum oxide to passivate these for the photovoltaic device, and I did an anneal on those to improve their passivation.
At the interface, have you ever do the plasma treatment before you bonding it, or you just do the kind of the bonding without any? Okay, I see.
No plasma treatment.
I see. I think that might help. So that is the kind of the useful, the conventional way. So yeah, I think that this is very interesting work. I'm very kind of impressed by those things. And then a few other questions is about your laser annealing of the metal oxide. So general question is that you see the kind of the significant improvement when you do the laser annealing of those metal oxide material, and then so I'm wondering what is the major effect in terms of material, like the kind of the point of view. It just improve the crystallinity or the increasing the grain size, or do you think there is any effect on the oxygen vacancy and the stoichiometry? So what is the major impact of those oxide material when it annealed by the laser versus the just furnace annealing? So what would be the kind of the major difference you think?
So one thing, so obviously, with the shorter pulse width, there's probably less time for oxygen to, diffuse in or out of the molybdenum oxide. Again, the increases here is moderate, but there is a definite increase across a wide range of fluences. So, it's not super high or anything, but for molybdenum oxide, I don't think crystallinity plays an important role for this one. I think it's mostly modifying the stoichiometry and sort of the work function alignment because it's entirely based on sort of its placement with the silicon absorber. So I think it has a role to do with that, but again, we need to look at yields or something to see, energy electron loss spectroscopy to see how that is changing with the laser processing.
Yeah, because one of the reasons is what I saw is the more like the results. So I was wondering if you kind of go deep into the material characterization, how does this annealing method affect to the some material parameter like the X-ray or the nanoscale, like the morphology or the stoichiometry or the. So I'm just curious what will play the major role for this one. So and then. The other question is because you're using the lasers, and then there might be the kind of the absorption, so kind of the temperature variation depending on the depth. So have you ever looked at the depth profile of the those composition or the some crystallinity in terms of the depth and then spatial resolution?
No, I wasn't able to. I did. One issue with the films is they're both, in this case, 10 nanometers thick. So, I mean, I can't do XRD or anything. Raman potentially, but I did some Raman on the molybdenum oxide. But most of the signal, I did this on glass. I couldn't get much signal besides the glass signal. So it was difficult to characterize it all. I definitely need to look into that more for the future study. This is just kind of a preliminary, I mean, not preliminary, but demonstration of the laser results.
I see.
It definitely needs more characterization.
Yeah, and the other question is, you showed a few video, and then I was able to see the change of the color of the those film. So is it because of you're changing the optical property, like the NNK will be changed depending on those annealing process?
Yeah, definitely. So, with all of these, you can see a shift in the optical properties as well. I showed the transmission change, but this one you can see a slight shift to a darker blue color.
So this is silicon, right?
Yeah, this is polysilicon that's shifting in color.
So what make those color shift? Is it kind of the surface morphology or the intrinsic like NNK property of the polycrystalline silicon?
I believe it's an NNK property, so that for the refractive index will increase substantially with the crystallization. So the N's pretty low at first, and then I think the N peak is around. Well, based on this, it's somewhere in that 300 to 400 nanometer range. This is the absorption depth, but N is also. Oh, wait, actually, you know what? I have that real quickly. Yeah, so refractive index of silicon is really high at around 400 nanometers, around 7. Amorphous silicon has a similar profile, but it's looks like this. So it's much more broad. So as it crystallizes, it becomes much more sharp, which is what I think it results in that color change. It's reflecting more light in the blue, and that's why it appears bluer.
But you're annealing the polycrystalline silicon, not the amorphous silicon, which means it's the kind of the grain of the like the crystalline silicon in different size. So I was curious if it is the morphological effect or the kind of intrinsic effect. So because the crystalline silicon has the kind of the stable NNK, you wouldn't change significantly like that way in terms of like even you could see the color change. So I was wondering if you take a look at the like the AFM type of the surface morphology observation before and after the laser annealing.
I didn't. We mostly relied on what these samples came from Georgia Tech, and so they've had this result. The as deposited film, they did a TEM, and it shows it very amorphous.
That is the cross section, right?
Yeah, right. Not
so
AFM.
I mean in the surface, in plane, kind of the morphology change.
In plane. I didn't look at that. No.
I see. I see. And probably the other question is that you think there will be the kind of effect to the activation of the doping, right?
Yes.
So do you think it will create the gradient doping? So because you have a more energy on the surface, so that it like the vertically the kind of the energy transfer from the laser to your sample might be different. So do you think the doping activation might be the uniform over there?
No.
Thickness, or do you think it will be a gradient?
It likely is a gradient, because the temperature profile is, different. The gradient's different. There likely is a gradient in the doping profile.
So when you do the kind of those device simulation, do you think those gradient doping would help for your device performance to create some field, or how do you think it will affect?
I think I want a pretty high doping right at the interface so that I get that induced band bending. So because sometimes
these dopant will diffuse into your active, like the medium from the highly doped, right?
It's a bit of a balancing act to prevent that. I want as much activation as possible, as close to the surface as possible, while preventing any dopant diffusion into the bulk.
I see.
Yeah.
And probably we'll just ask one more question. So have you ever kind of measured your laser beam uniformity in terms of like spatial resolution? Like so is it kind of Gaussian like the kind of the energy distribution, or that is kind of fully collimated and uniform over the whole area of your beam? How does beam kind of energy profile looks like? Yes, I have that data. I didn't include that in the thesis, but we measured it before. It is a Gaussian profile, but because it's a diode pump solid state laser, there is a bit of ellipticity to it. So there's a fast and slow axis in the beam profile. But I mean, from the SEM, you can see here, it's hard to tell that it's occurring. So, the beam profile looks nice and Gaussian. Yeah. I see. Okay, so I think that's it from me. So thank you very much for the nice presentation. I really enjoyed it. Thank you.
Okay. Can you go back to slide 25, please?
Sure.
You say this is optical modeling. Did you model it, and how did you model it?
The data was actually taken from SOPRA SA. It's they have all the different materials and different optical values. I didn't list that here, sorry. But I think I did put it in the thesis.
Okay,
Yeah.
got it. So that's okay. We already talked about Raymond. You mentioned Hall measurements, I think a few slides, 29.
Yeah.
Can you say a little bit more about the Hall measurements? Did you do them at UVA or someone else?
Yes, we have a Hall measurement system from Acopia. Basically, there's a 4-probe measurement system. The 4 probes go in the corners of the sample. And then you place it in, you place it sort of in plane with a magnetic field, or perpendicular to a magnetic field. And you measure the conductivity between all the different probes, and then it gives you, based on that, and then you flip the magnet around and try it again, and it can give you the dopant, how the dopants drift, and the dopant type and the dopant concentration from that, as well as resistivity and conductivity, things like that.
Great. Yeah.
It's a pretty simple measurement.
So yeah, I'm as well interested in the bonding, and I have a few questions on the bonding process. To start with, on your slide 55, you mentioned that work from 2013 with the absorber layer. So what was the problem in this? Do you know what the problem was in this paper?
So that works well for bonding, but I think their absorber layer was made of gold. And obviously that's going to throw off any, I think it was gold, it could have been carbon or something, but it's going to destroy any PN performance between the 2 wafers. So if you have any material at that interface that isn't silicon, it's going to mess up the PN performance between the 2 wafers.
Did you know why they just wanted to demonstrate the bonding, or what was the purpose of this structure?
I guess so, to demonstrate laser bonding, so reduce temperature, just to bond 2 wafers together. I don't know, I don't remember what the final device was for. I think it was just for MEMS packaging or something.
Okay, got it. Yeah, because I mean, it sounds interesting that you actually can place a different material sandwich between silicon, for instance, right?
Right.
Where you may be able to manipulate the band gap. But you think, so assuming it's not gold, but something else, a semiconductor, do you think that could work as well, or?
So one of the things I was thinking about initially was maybe putting like a thin layer of amorphous silicon on top of the wafers. But the problem is for amorphous silicon, the band gap's 1.8 EV instead of 1.1. So it would absorb even less of the 1064 light, although it would melt easier, but it wouldn't absorb the laser light that I needed it to. I guess you could use a material. I guess what you need is a semiconductor that can absorb the laser light from E1064 or maybe somewhere in the near infrared, but also still has semiconductor behavior. Maybe there's material, but I think it might throw off the PN performance.
So, well, I guess one could use a narrow band gap material, right? Would that make sense? Would that work?
Narrow band gap. Yeah, I think that would work. Yeah, if I'm understanding correctly. You mean like so higher EV or lower EV?
Yeah.
Well, because then the light will transmit through it, right? The infrared light.
Okay.
I get confused exactly what.
Yeah, I'm wondering what this method may open up, right, in the future. So if you can bond different materials together using this approach, I'm wondering if that can even work. I mean, clearly you need the absorption at the interface. So it may not work with narrow bandgap, right? Because yeah, maybe that's something to think about.
Okay.
I was wondering if you actually need to bond the surface, well, both surfaces completely. I think what you did was line by line,
Right.
spinning the laser. is that, so that gives mechanical strength or makes the mechanical bond, right? So that the
Mhm.
two wafers stick together. Are those the only regions where you may actually form a p-n junction, or what's between these lines going on? Or
I'm not
what's
sure.
the expectation?
I guess there could just be air gaps there, which obviously is not good. It'd really be helpful to see the interface with TEM, do a cross section at the interface between the two.
Yeah. So the goal would be really to kind of completely bond both pieces, right?
Right,
Basically not doing or have overlapping lines where you scan your laser, right?
right.
Something like that.
Uh-huh.
Okay.
Yeah, or maybe as Professor Lee was saying, use a defocus beam in a huge spot or something at a very high power to sort of fuse the two together. That might work as well.
Right. How did you make sure that you actually see a p-n junction, or not just some Schottky contact from your probe needle or something like that?
So I based it on the VOC mostly. So with just the wafer stacked, the knee voltage is quite low. I'm not seeing any and then also it's very linear at the higher. I didn't show this, but at higher voltages, it just at higher voltages in the positive, quadrant 1, it just becomes linear. Whereas for this one, my VOC is 652 millivolts, which is relatively common, or is okay for a silicon solar cell, relatively okay. And then it has a diode shape. I didn't show it, but it continues to curve, and then in quadrant 1.
Okay, so basically comparing this curve with the one on the previous slide where
Yeah,
you just stack them.
right.
So how do I have to think about stacking? Is there any force, or, I mean, how can you even get a rectifying behavior here if they just kind of, well,
There is some force from the probes. I'm using sort of a spring-loaded probe, so they're kind of pushed together that way. But yeah, you're just sort of just to see if I could get from the stacked, if I could get any sort of rectifying behavior, and then again, if the light would cause any increase in the current there, which it did. I just wanted to make sure that what I was doing was not just based on stacking, but was based at a much stronger photovoltaic response than just stacking the two wafers.
okay.
Yeah. But yeah, I didn't quantify the force that it was pushed between the two.
Yeah. Did you check if both, I mean, obviously these are just, I guess, centimeter-sized wafer pieces, right, that you put together. Did you check the surface condition in terms of how planar those surfaces are to each other, or something like that? You mentioned air gaps, so I'm wondering if, I mean, sometimes you have to work with wafer bow and all these things, and was that an issue here?
No, I did. I mean, so I could have, I guess, picked up some of the RMS roughness with Zygo, but I didn't look at that. It's still bonding without really. I wasn't too careful with the surface. How the surface was clean, but I wasn't super careful with how clean with plasma treatments or anything like that. And it still was able to bond. I did this 3 or 4 times with different samples. So you can be relatively uncareful and it'll still work, which was nice. But I'm sure I could improve it much further if I did this in the clean room and I did all these plasma treatments to keep the surface nice, and also looked at the bowing of the wafers.
Right. Yeah. I'm wondering if it, I mean, if it just sticks together because it's kind of, you have a bond somewhere, right? Or if you actually have some nice contact between the two. I guess that's my point, and that's going to be interesting to look at, either in a cross-sectional kind of. I guess that's what you're going to do. Yeah,
Right.
cleave it, or and then look at the cross section, but then also take it apart and see it. Take a look at the surfaces. Is there any other way to verify that you actually have a p-n junction?
Versus
How could you measure that versus something else, I guess?
like a Schottky junction, or is that?
Can you measure capacitance, for instance, on such a bonded device?
I suppose so. I didn't look into that. I don't know what it would actually look like. I did some work with the metal insulator semiconductors, but I don't know what two semiconductors would look like CV. I guess it would just be sort of this sort of shape, but I'm not sure. I didn't look into that.
Yeah. No, it will actually look different, but yeah, maybe that's something you can check. You said that the series resistance is limiting here. Where's the series resistance? Where do you think it comes from?
So yeah, it's roughly 700 ohms. There's a few things that could be happening. One, my spot, if you look at this, is roughly 3 to 5 microns, the pulse width, because of the high NA lens. So there's really not much bonded area. Also, because I used water, some of these bonds could be, silicon, oxygen, silicon bonds. And obviously those will be resistive. And yeah, so I think those are the two major sources that I can think of. So like a small bonding area and, oxygen in these bonds could cause a higher series. But yeah, it causes this sort of loss in fill factor here.
Okay, and that would be solved once you bond or kind of cover more completely the surface with your laser. Would you think that solves that issue, or?
It would have more complete bonding area. I think that you could get definitely a higher current and hopefully lower series resistance. But as long as I'm using water, it might be difficult to get a really low series resistance because of those SiO-Si bonds that'll form.
So we're not talking bulk bulk resistance. You think the resistance only occurs at the interface?
So the resistivity of the top wafer is like 1 to 5 ohm centimeter. The bottom wafer, obviously being P plus type, it's like 0.01. So it's really very conductive, the B plus wafer. The N wafer is a little more resistive, but I don't think it would cause, those are typical wafers used for, solar cell fabrication, that type of resistivity. So I don't think that's the cause of the high series resistance. Typically, they're usually in the one ohm range for a device, solar cell device.
How thick were the two wafers?
280 microns, both were identical thickness.
Yeah. Okay. Well, that's an interesting approach. That's going to be interesting to study further. I don't have anything else. Are there any other questions, comments from the committee? Well, if not, then the committee will discuss a couple of minutes, and I think I can put people in waiting rooms. So audience is, I think, is welcome to stay, but I gotta put them in waiting rooms, including you, George. Okay.
I'll stop my share.
Right.